Thank you. So I will talk about JumpSwitches, and we'll start by talking about Spectre. This is a security track, so I'm sure that you all know about it. But Intel CPUs and other CPUs were found to be susceptible to all kinds of speculative execution attacks. And in this talk, we'll talk about Spectre, and just briefly to mention what it's all about. So Spectre is a family of vulnerabilities. And basically, the main cause is that CPUs try to execute instructions as fast as possible. But from time to time, they encounter an instruction that prevents them from knowing what the next instruction to execute is. In such case, CPUs try to guess. And when they guess, they use a branch predictor to guess what the next instruction is, and they might mispredict. This misprediction, we are told is benign, and we are told not to worry, but it turns out that even when we discard the results of this misprediction, there are side effects that affect resources of the machine, specifically caches, for example, and a malicious user may manipulate the CPU in order to run a flow of instructions that speculatively that will expose and leak data that it should not know. Later on, by timing accesses to the caches, it can infer what the information is. So Spectre v2 that this talk will revolve affects indirect branches on Intel CPUs. And it turns out that on Intel CPUs, you can take an indirect branch, like those that are being used by function pointers, and manipulate it so speculatively you will execute arbitrary piece of code that exists in the privileged domain, in the kernel in our case. Even if this piece of code should never be executed by the indirect branch, even if it's not this one of the two do good or do no evil functions that are executed by the function pointer. There is a solution, and the solution that is being used today is called Retpoline. And Retpoline is a solution that was developed in Google, and the idea behind it is to emulate the indirect branch using a different flow of instructions that prevents speculation. And this is good because it prevents the attack, but it is not that good because it induces overheads of tens of cycles for each indirect branch. Each indirect branch is effectively mispredicted. So the main idea behind our solution is a common technique, which is called indirect branch promotion. And to explain the basic idea, assume that we do have some function which is called doHot, and we know that this function is the one that is usually executed by an indirect branch. We can precede the call to the Retpoline with a piece of code that checks whether the function pointer that we are about to use is indeed this doHot function, and in that case, call doHot using a direct call. Direct call is a call in which the target of the call is encoded inside the instruction and is not susceptible to Spectre v2 attacks. If we fail, if that's not the case, we just fall back to Retpoline. Now, indirect branch promotion might look like a great solution, but it has some problems because hot functions might be different in different systems, on different workloads, and might even change a long time. So profiling and rebuilding anyhow is a partial solution at best, but even then, this is not a trivial task for a random user to profile his workload. When we talk about operating system kernels, there is usually, most distributions provide you a single kernel, and you are not about to profile it and rebuild it in a way that is something that the users might do. So we need a dynamic and adaptive solution, something like JIT, and that's what we are doing basically. So this basic inline jump switch that we show is based on two stages. The first stage is a stage of profiling, and the second stage will be a stage of binary rewriting, and all of those two stages happen on the fly. So initially, we precede the code that calls the Retpoline instead of an indirect branch with some kind of code that saves the branch source and target for each one of the branches. In this case, every branch is basically falls back to the Retpoline, and we have misprediction. After we collected enough samples, we start to collect the samples and perform binary rewriting. So basically, on the fly, we change each piece of code that preceded the Retpoline into this indirect branch promotion code. Now, there are advantages. The basic idea is simple, maybe, but doing it correctly is more harder, and I'm not going to get into the implementation details too much. But we do want it to be easy to deploy, so we provide a compiler plugin, which makes it all kind of non-intrusive in a way. We still require a worker thread that would do the hard work and figure out what the branches are, where do they lead to. We employ efficient sampling and patching in order to avoid overheads during the learning stage, and we have support for multiple hard targets using an outline block because we don't want to reserve a big piece of code just for the worst case scenario. Now, after we developed this mechanism, we tried to measure performance, and we still saw that there are many branches that we do not manage to predict correctly, and we do have overheads for them as well. And one of the cases we encountered is the case of system calls. Now, system calls is challenging and it is important because it is a common indirect branch that is mispredicted. Every invocation of system call requires a jump table, so basically this is an indirect branch and which is mispredicted. There are two main problems in this case. The first problem is that we have many potential targets. There are many system calls. And our inline jump switch that I just showed can handle one, and we have a mechanism that can handle few, but basically we are going to have a lot of misses. And beside of that, we have the problem that, the second problem that we have is that different processes might have a different distribution of system calls, and we need to handle these cases as well. The kernel code is mutual to all the processes, so this is not that simple. So for the first problem that I just showed, we employ search jump switch, we call this solution. And the idea is to use index mapping to map system calls to indexes. So we take the system calls, we learn what they are, which system calls are frequent, and the most frequent ones are being mapped to indexes between 0 and 2 in the power of something, which is 4 in this case. Those system calls will be executed through a binary tree. The other system calls, which are more infrequent, are mapped to nil, and we will execute them through a jump table. So it looks pretty much like that. System calls, system call like accept, for example, let's assume it's a frequent one, will go based on the index mapping to binary tree, and another system call like send to will go into jump table. And eventually it works like that. We have the index mapping, and whenever we get an accept system call, we are going through a binary code, a binary tree, which is actually a piece of code that is laid out in memory. And we traverse through the tree and eventually go to the direct call, direct jump in this case, that goes into the system call. If we get a system call which is frequent, we fall back and go to the Retpoline. Of course, we have a worker that looks what system calls are frequent. From time to time, we do profiling and update this binary tree and index mapping. The second problem that we had is the fact that each process has a different, might have different system call distribution. We deal with it by learning the targets per process. But we still need to deal with the fact that the kernel code is mutual to all processes, and we just break it, and we take one code page out of the process and make that each one of the processes would have a different kernel page. The trampolines that we use to call the system calls, the binary tree, which is a piece of code that is laid out, and the binary patching, and are per this kind of per page, per process. We have one challenge, which is x86 challenge, that we need this code page to be adjacent in the same 2 GB area as the other pieces of the code, and we deal with that as well. Finally, the last problem that I will talk about is the call chains. And for this reason, we are using registration JumpSwitch that I will present next. But let's assume for the second that we have a call chain. And let's assume that this call chain does not change very frequently. Again, this is based on actual, and I will show later on, things that we saw in the Linux kernel. If we have a call chain and we have this kind of invocation that goes through each one of the call chains and calls it, we have a problem. We can handle very nicely, as we saw before, using this inline jump switch, a single indirect call that turns to be a Retpoline. We can use indirect branch promotion. But when we have multiple ones, they are being invoked in a loop. And the problem that we have is that in this case, the source, the indirect branch that jumps to each one of those destinations, to those targets, is actually the same indirect branch. So we are going to have many misses. But in this case, we also see that the pattern of the calls is very expected. And for that reason, we are using not a transparent mechanism, but we provide a registration code. We allow you to perform, to explicitly say that whenever the list, the call chain changes. And in that case, perform binary rewriting. So each one of the pieces of the code will go to the right target. And we do not need to have any Retpoline fallback for that case. We implemented all of that on the Linux kernel, and we see here multiple benchmarks that we executed. Sysbench and dbench are file system benchmarks. Nginx and Redis are network benchmarks. The y-axis shows the speed up, and this is a lot to grasp. So I will go a bit to more concrete points, but just to emphasize that on the purple color, we see what is the baseline performance, the performance of a protected system today. On the red bars, we see an unsafe system, which is a system that is like the optimum that we want to achieve, which is actually a system which is unprotected without any Spectre v2 mitigations, without Retpoline. So the first thing that we can see is that inline jump switches provide most benefit in most cases, not in the case of dbench, but in others they do. And this is the basic mechanism that we saw initially. The second thing that comes out from these results is the dbench, the file system benchmark that invokes a lot of system calls of different types, gets a 3% performance improvement from the search jump switch that looks through a binary tree to use a direct call in order to jump to the right system call. In the case of Redis, the case of Redis is interesting. It turns out there is a system in Linux that is called secomp, which is a mechanism to provide a user space to define system call filtering, saying that some system calls should not be executed because the application does not need them, and therefore they should not be executed if by mistake a process is being compromised. Secomp is nice, but it turns out that when you attach many filters, each one of these filters that say whether a system call should be executed or not is being invoked using an indirect branch. In the case of Redis, we saw that 17 indirect branches, 17 filters are being invoked whenever you run on our Ubuntu system, Redis. So the registration jump switch provides us a 2% performance improvement as well. Eventually, we get a speed up of 10%, up to 10% performance improvement, and we are less than 2% performance than unsafe. So as we saw, jump switches dramatically reduce the Spectre v2 overheads. We submitted patches to Linux, not of all of our work. We are waiting for some things to result. And I think that it is interesting to see that binary rewriting, although it's being superseded many times people say by virtualization and other solutions, can still improve performance significantly in some cases. That's it.
Hi, Tom Spink, excuse me, University of Edinburgh. Are there any additional security concerns that arise from indirect call promotion?
Yes, thanks for the question. I left it because I knew somebody will raise it. So basically, there is one issue which affects, so there is an issue of Spectre v1. So the fact that we use indirect branches might look dangerous because, not indirect branches, sorry. The fact that we use conditional branches might look dangerous, but you need to remember that actually every direct branch that you have today in the system is susceptible to Spectre v1. And so just to say, there is a different flavor of Spectre that usually people think affects only conditional branches, but it can cause type confusion, and it also affects indirect branches. So unintentionally, Spectre v1, basically, if you know what you're doing, you can mitigate it relatively well if you know what you're doing. That's another question. But indirect branches are susceptible to Spectre v1 regardless to our work. At the moment that Intel resolves Spectre v2, they are not about to solve Spectre v1. The CPUs still will be susceptible to Spectre v1, and mitigations will need to be set to prevent that. So the fact that we do not, our system makes the system susceptible to Spectre v1, but we rely on the fact that other mitigations, as some were adapted, will prevent that, if that's what you regarded. Otherwise, I just gave you some material.
Okay. Did you have to justify that to the Linux kernel folks when you submitted it?
No, we needed to justify to the PC committee, to the program committee. But the Linux people did not have this consideration. They actually implement something similar, which is more static right now.
Right. Okay. Thank you.
Well, go ahead.
Hi, nice talk. Siwan from Dankook University. Have you ever thought about how to work with integrity management?
Can you repeat? Work with?
Kernel integrity, code.
Kernel integrity? You mean like the fact that we patch the code, the binary rewriting is a consideration, yes. Right. So binary rewriting is a consideration. I have a couple of answers for you. So first of all, it's being done today. Okay, so today you already have rewrite of the code. For example, if you have a single core system of Linux, you boot it with the single core, then you hard plug another core. You have that happening that all your x86 instructions which do not have lock prefix, all of a sudden will have lock prefix without your knowledge. And there are many other cases. This is just the easy case to explain. Okay. The second thing is that the mechanism that does it, if you saw it, you would be really concerned. So we try to improve it, and I think that in the next Linux version you will see that it's better. Not that you will notice, but it is safer nowadays because we did work also in order to improve this kind of thing.
Okay, thanks.
All right, I had a question. So Intel's coming out with a new instruction, if it's not out already, which is essentially a branch prediction barrier. And so between that and other features where they're going to like isolate the BTP between hyperthreads, is there an advantage to JumpSwitches over that upcoming approach?
So very good question. I think that it's hard to say. I think that I don't know, to begin with, I don't know whether speculation will actually be prevented with this extension. Spectre v2 is about to be mitigated completely, let's put it in the future Intel CPUs. We saw up to 2% performance improvement, but even without, when we disabled all the mitigations in some cases. I didn't want to show these results because actually the benefit is a bit marginal to be confident about the worthiness of this approach in such cases. But I think that with some kind of refinement of the mechanisms, there might be a much smaller benefit for this approach as well.
Okay, thank you. Any other questions? All right, well then let's thank our speaker.